Hello and welcome to Megagon Labs sponsor session at Sigmod 2021. My name is Astava Mrushka, and in this session I want to tell you a little bit about our research lab, the work we do, and also I would like to introduce you to Bazat and Julian, two of our senior research scientists that will tell you more about two papers that they are going to be presenting during this event. Megagon Labs is a research lab, and we work with different type of approaches and models related to artificial intelligence, machine learning, natural language processing, data management, and the intersection of all of those areas. The goal of our lab is use this type of technology to empower people with better information to make their best decisions. The types of applications that we develop or that we focus our models are based on experience discover and search, data analytics and exploration, knowledge representation, knowledge discovery, data preparation, data integration, and so on. We are located in two offices, one office in the Bay Area in Mountain View, California, and the other Megagon Labs office is in Tokyo, in Japan. We are an innovation hub, part of the Recruit Holdings. Recruit Holdings is a Japanese company that was founded in 1960, has revenue around $21 billion per year and market capital of $50 billion. Recruit Holdings provides over 200 online services in many different areas, such as human resources, travel, housing, education, restaurants, and many others, in which people make daily lifestyle decisions. Many of our subsidiaries are well known. Here are some examples of companies that are also under Recruit Holdings. At Megagon Labs, because we have the opportunity to be close to so many of our subsidiaries, we have also the opportunity to work with different problems and a huge amount of data related to such problems that can take advantage of machine learning, natural language processing, data management in general. We are surrounded by many different types of data, and one of those is what we call user-generated content or user-generated data. This kind of content can be reviews for products and services, can also be found in terms of community question answers and many other different ways that users in general can add their opinions or can add their own data. A number of different interesting and relevant tasks can be explored using this kind of data, such as review retrieval, review summarization, contrastive review identification, knowledge-based construction and population, and so on. For this talk, I will focus more on reviews that are generated by users for services, products, and so on. Using this kind of data actually presents to us very good opportunity for exploring and proposing new approaches, new methods, new models based on machine learning, information extraction, natural language processing, data management, and etc. Some specific characteristics of this type of data are they are rich on subjective and opinionated facts. Their relations or the relations that we found are actually not very explicitly. In many cases, we, to extract knowledge from this kind of data, need to read in between the lines and go beyond simple approaches from traditional models from natural language understanding. Because of these characteristics, at Megagon Labs, we decided to start some approaches to help us creating better representation of this kind of data. One way to try to better represent reviews is by using aspect-based sentiment analysis. So for example, from this text here, we can, based on the sentence, the elevator was a bit slow, breakfast was not very exciting, room was small, we can extract some aspects and opinions. For instance, for the aspect elevator, we can consider the opinion being a bit slow, which is a negative one. For breakfast, not very exciting, also negative, and so on and so forth. Based on this kind of extractions, we can better represent reviews and use them in a number of different downstream tasks. So one of the projects that we had in our lab was called Snipex, and it was focused on extracting aspects and opinions from reviews. One of the characteristics of the model that we proposed, SNPExt, is that we try to avoid or overcome one of the most challenging aspects of this, which is how to find label data to train machine learning models to make good extractions of aspects and opinions. In SNPExt, we use the idea that from a small initial set of label training data, we could generate more examples through data augmentation. And we also explored the idea that both labeled and unlabeled data could be used to fine-tune an in-domain language model, and thus getting better results for the aspect opinion extraction. SNPExt was published in the Web Conference 2020. The main idea is to use a language model and feed it with an initial small set of label data plus an extra set of augmented data that is automatically generated, and in addition to those, also use the unlabeled data to help the model to get better results on the extractions. For the sake of the time, I will not go into much details of the model itself, but I will show you that with that proposal, we achieved the state of the art in a number of different benchmarks. We have available a demo for SNPExt, and if you're interested, please visit our website, megagon.ai. Okay, we got aspects and opinions from a bunch of text, let's say from a set of reviews. So what now? Once we have this kind of aspect and opinions extractions from the text, we can now use it in different ways to help us to better understand reviews and also to help us to apply it to different downstream tasks. In today's talk, I will explore review two different ways that we use the results from SNPExt applied to reviews data. The first one is using SNPExt for sample. Sample is another project that we had at Megagon Labs. It was published last year at AKBC, and it's a domain-independent, unsupervised knowledge-based construction for opinions and implications. The main idea of sample is that we can explore aspects and opinions that can be extracted from text, reviews in this case, and then build a knowledge base that can represent implications from the opinions. Consider as example the two reviews. Review 1 saying the movie has everything, fast-paced action, romance, and complex characters. And review 2, there is some pretty good writing going on. Based on those two and using our approach, we can identify that complex characters can imply pretty good writing. Based on the identified implications, sample can now be used in the construction of knowledge bases. And we showed in our examples that it can beat state-of-the-art models in specific benchmarks for knowledge-based construction. You can explore sample following this URL and checking our demo. In addition to use aspects and opinions to represent the reviews and building knowledge bases as we did in sample, we are also using this kind of information to create internal representation for reviews. And based on this, we can have better ways to explain what is going on in a review and help users to take decisions. Explain It is the model that we created at Megagon Labs to do that. And I'll show you a little bit more of details about it. So the paper was published this year at the Web Conference, and its title is Constructing Explainable Opinion Graphs from Reviews. In Explain It, the main idea is that based on aspects and opinions, we can generate explanations for the opinions generated by the users. And in this sense, we can help other users to understand better why, for instance, a hotel is considered to be in a great location, and so on and so forth. So in this sense, the users can explore the reviews going beyond just simple personal opinions, but also trying to identify what were the facts that explain why an opinion is given for a specific aspect. Let me show you an example so we better understand what type of results we can get using Explain It. So imagine you are trying to select a hotel to stay for the night, and you want to check a few of them. And for the first one you are going to try, you see that there are more than 3,000 reviews to explore so that you can understand what the other users that stayed in the hotel would think about this. So instead of going over all of those reviews, if you use Explain It, it will provide to you different ways to analyze and and interact with the system so that you can really learn much better about the hotel in this case. So the first thing that we have in explain it is that it is also based on aspect and opinion, so it will highlight for you aspects that were found in different reviews of this hotel. In addition to have these aspects highlighted here, we also generate a textual summary of all the reviews based on those aspects. In addition to that, the user can also select a specific aspect and read the original reviews based related to that kind of aspect. But the most important characteristics of our Explain It model is that it shows in a graphical way an explanation for the opinions and the aspects and opinions that are extracted from the text. Consider in this case that in addition to tell the user that there are lots of homeless people surrounding the hotel, the explanation for this type of aspect here can be originated because the hotel is in a bad street and it's not the greatest area of the city, and then as a consequence a lot of homeless people are around. Another interesting one for this hotel specifically is that this is considered a nice hotel, and the explanation for that is because the staff is friendly. There is an old lady at the front desk, and also the front desk is considered very helpful. So with this kind of information and graphical explanation, the user can with much more easiness explore the reviews and understand whether this hotel is its better choice for staying the night or not. With this, I will finish this introduction part of our session today, and now I will ask Julian and Beza to talk a little bit more about the projects that originated the two papers that they will be presenting during SIGMOD this year. Thank you very much and enjoy the conference.
Welcome again to our sponsors talk. My name is Yu Liang. I will present our work Rotem. This is joint work with our colleague Caroline and our summer intern Zheng Jiemiao from Duke University. As we mentioned, Megagon is the research arm of Recruit Holdings, which has many subsidiaries such as Indeed.com or Glassdoor.com, covering domains from HR to education. You can imagine that with data from so many subsidiaries and applications, there are many interesting research challenges in data integration, knowledge bases, and natural language processing. So here are a few example projects that I have been working on in the past few years. The first project I did in Megagon is subjective databases, or OpenDB. In OpenDB, we built an extraction pipeline that extracts subjective opinions such as very clean room or good work-life balance from hotel or company reviews. We then aggregate these extractions into subjective attributes such as histograms about cleanliness of hotels, which can later then be used for query answering or data visualization. Or by looking at the co-occurrence of these extractions, we can construct a knowledge base that captures their correlations, such as the concept thin wall being correlated to the concept noisy rooms. I have also worked on the problem of entity matching. Entity matching refers to the task of checking if a pair of entity records refer to the same real-world entity. We also extend this problem to a more general setting of matching entities of different types. For example, matching resumes with job postings such that the resume is qualified for the job. We would like to generate explanations in addition to the matching results for this because this application can really impact people's life. By doing so, we are answering to the call for responsible data management. A common theme we observe in this project is that machine learning, particularly deep learning, contributes significantly to the success of the project. However, this is the case only when there is sufficient amount of training data. Deep learning is data hungry. For example, in computer vision, the best image classifiers are trained on ImageNet of 14 million labeled images. In NLP, training the best question answering model requires a Squad 2.0 dataset of 150,000 query pairs. In many other applications, such annotated datasets might not just be not available. So for every new task or new domain, we will often need to label, say, at least thousands of new examples, which can take a significant amount of time or money. To address this issue, data augmentation has become a common practice when training machine learning models. The goal of data augmentation is to perform data transformation to generate more training examples from existing ones. In computer vision, one can apply transformations such as rotation or flipping of an image and get new examples with the same labels. The model now can learn invariance properties such as a rotated cat is still a cat. Similarly, in NLP, we can use transformations such as word deletion, synonym replacement, and expect the meaning of a sentence to stay unchanged. In Megagon Labs, we have seen many success stories of applying data augmentation to data management and natural language processing tasks. However, although DA is shown to be effective, there are several technical challenges that we need to address. The first challenge is that DA may corrupt the labels of the sequence or fail to generate diverse examples. In this example of query intent classification, the original sentence where is the orange bow is asking for a location of an event. If we delete the token the, it looks okay, but the model might not learn much more new information. If we replace where with the word the or what, then the sentence becomes asking about information or description, so the original no label no longer applies. Now if we want to apply multiple operators at the same time, the sentence can be more diverse, but is more likely to get the wrong label. The second challenge is the inefficient process of DA. In the standard process of applying DA, a developer usually picks an operator at a time, chooses its hyperparameters such as how to replace tokens, and then trains the target model. This tedious process may have to repeat multiple times, but ended up with only suboptimal results. This situation becomes even harder when combining multiple DA operators, which simply blow up the search space combinatorially. To address these two challenges, we propose Rotom, a multi-purpose data augmentation framework that trains high-quality machine learning models only using a small number of label examples. To address the first challenge, we propose a novel seek-to-seek based DA operator called InfDA. By doing so, we can generate diverse data augmentations by allowing the operator to modify arbitrarily many tokens at the same time. We leverage a novel distance supervision technique to train the seek-to-seek model without any labels and to guarantee the high quality of the generated sequences. And for the second challenge, in order to reduce the effort of tuning hyperparameters, we develop a meta-learning framework that automatically learns how to select and combine the best example generated by multiple DA operators. Our framework jointly trains a filtering policy and a weighting policy models together with the target classification model, so that we can efficiently train all three models at the same time without much hyperparameter tuning effort. One nice property about Rotom is that by having a simple problem definition of sequence classification, Rotom can support a range of data management and NLP tasks, including entity matching, error detection, and text classification that can be cast into sequence classification. Rotom achieves very significant results in our experiments, as it can outperform the previous state-of-the-art in entity matching by over 4% F1 score using only about 6% of the original labels. For error detection, we outperform the previous best method based on active learning by 7.6% F1 score on average using strictly less trained examples. And for text classification, Rotom outperforms two recently proposed data augmentation techniques in NLP in the setting of low-resource text classification. If you want to learn more about this work, please come to our paper in the session Machine Learning-Based Data Management. You can also check out our upcoming tutorial, Data Augmentation for ML-Based Data Preparation and Integration via DB this year. Thank you.
Welcome to this part of our sponsored talk. My name is Behzad and I'm going to talk about Darwin, one of our projects at Megagon Labs, which is also presented in this conference. This is joint work with my colleagues Sayam from University of Massachusetts Amherst and Wang Chu, who is now at Facebook. As you have heard in the presentation so far, Megagon Labs works on a wide range of problems related to data integration, knowledge bases, and natural language processing. Of course, machine learning and deep learning techniques are a big part of our solutions for various problems in these areas. And it goes without saying that such techniques are data hungry, and collecting the required data can be costly and time consuming. To this end, we are working on various projects at Megagon Labs to facilitate the process of collecting labeled data and getting the most value out of it. The project Rotom, which my colleague Yuliang discussed, is an example of such project, which enables us to develop better models using a small number of labeled instances through data augmentation. In this part, I'm going to present another project, called Darwin, and which in a nutshell is a framework we have developed to generate large amounts of training data for NLP applications with minimal cost. To introduce Darwin, it will be good to start with an example of a labeling task. What you see on the screen are a few examples of messages exchanged between hotel guests and the front desk staff. And we're assuming that in this labeling task, we're interested in labeling messages in which guests are asking for directions from one location to another. For instance, maybe from the hotel to the airport or vice versa. The green color highlights messages that are asking for directions and should be labeled as positive, while the rest are negative examples. Now, it is important to consider that guests exchange messages about many different topics with the front desk staff. So asking for direction makes up only a tiny fraction of the entire corpus, something like 4% or less. In this case, sampling data randomly and labeling it is very inefficient, as most labels will end up being negative. To address this issue, we can rely on distant supervision techniques, which in a nutshell label the corpus using a set of labeling rules. For instance, looking at exchange messages, we might conclude that any sentence that mentions SFO, which is an acronym for San Francisco Airport, should be labeled as positive. Of course, the rules can be noisy, but there are existing techniques for denoising labels and using them effectively in training. But it turns out that writing labeling rules can also be very difficult. For instance, let's say that we are convinced that any mention of SFO is a good rule for labeling a sentence as positive. Now we have to test the coverage of this rule. Are there 100 sentences out there that mention SFO, or maybe just one or two? Assuming that it gives us a good coverage, we have to ask, is it accurate enough? Maybe there is a message saying we are on our way from SFO. In this case, labeling this as positive would be incorrect. Finally, what happens if we want to express a more sophisticated rule? How can we say something like we are interested in sentences ending with a question mark that mention airport, where the mention is a descendant of the word from in the dependency parse tree of this sentence? Writing rules as complex as this one require experts who are familiar with the rule language. Now let's talk about how Darwin facilitates the process of writing rules. Using Darwin, one can start with a couple of positive instances, and then Darwin automatically suggests labeling rules. Instead of writing rules, the annotators should verify a suggested rule, based on the few examples that match that rule. The figure on the right shows how the rule and a few matching examples are presented to the annotators. In this case, by looking at the 5 provided examples, we can guess that the suggested rule is likely to be effective. Note that by using Darwin, the annotators don't need to learn the rule language anymore. Moreover, they don't need to iterate over the data to come up with rules. And finally, they don't need to care about precision and coverage of rules, because Darwin automatically selects rules that are high coverage and are likely to be verified as correct by the annotators. But how has Darwin come up with candidate rules? In the interest of time, we're omitting a great deal of details here. But basically, it uses two key ideas to select candidate rules. The first is what we call the hierarchy of rules. Basically, any rule can be generalized or further specialized. For instance, the set of sentences that mention the phrase from SFO are a subset of those that mention only SFO. Now, note that if a rule is good at capturing positive instances, then all its specifications would be useless, as they do not contribute more to the coverage. On the other hand, if a rule is not so effective at capturing positive instances, there might be specifications of that rule that can be effective. Darwin uses these observations to guide its search to recommend rules. The second idea is to iteratively train a classifier based on the labels collected up so far in the process. The classifier enables Darwin to make conclusions about other sentences that are similar to sentences that are labeled so far, but doesn't match the existing rules. For instance, the sentence, how can I get from SFO to the hotel, and best ways to get from LAX to your motel are very similar, although our discovered rules may not match this statement. Based on this similarity, Darwin may conclude that any sentence that mentions from LAX is also likely to be positive, and thus suggest this rule to annotators. The combination of these two ideas is what allows Darwin to recommend effective candidate rules. Now let's look at how well Darwin works in practice. Here you can see our experiments on 4 different classification tasks on 4 distinct datasets. The solid black line corresponds to Darwin's performance, and the other lines correspond to a number of baselines, which we don't discuss here in the interest of time. But perhaps the most important thing to take away from this plot is that we observed that on almost all datasets with roughly 100 annotated rules, which you can see on the x-axis, we obtain an F on a score of 0.8 or higher, shown on the y-axis, which is great for training a classifier on especially for training a classifier, especially once the collected label are denoised. At the bottom, you can see how Darwin uses the rule hierarchy to start from a rule such as best way to get to, and start generalizing it and specializing it as necessary to obtain a new rule, shuttle to, which turns out to be quite effective at discovering instances asking for directions from the from the front desk staff. On that note, I'd like to conclude this presentation and thank you for listening. The official session for presenting this work was earlier this morning, but you can check out the recorded presentation if you'd like to find out more. Also, you can join us at the office hour associated with this paper through the Whova app, which is going to happen today, June 23rd, on 3 p.m. Pacific time. Once again, thank you for listening.